In the last video, we talked a little bit about some of the qualities that a good component should have. In this video, we're going to talk about specification. It helps to think of a specification in contrast to an implementation. Every software component should have both a specification and at least one implementation. The specification tells you what the software component does. The implementation tells you how the software component does it. In order to use the component correctly in your system, you should only need to know its specification. In other words, you should not have to look at the details of how it is implemented. Of course, for your system to actually run and run correctly, you also need to include an implementation that correctly satisfies the specification. We're going to divide specifications into two broad categories: informal specifications and formal specifications. An informal specification describes what a component does using natural language, like English, and perhaps using pictures or metaphors, things that help human beings like you and me understand what a component should be doing. Here's an example of a stack interface, and here is an example of an informal specification for that interface. As you can see, this is similar to what you'd find in a Java doc for the stack. As you may have noticed, the example is written in a language that is not quite Java. In Java, you can't have constructors in your interface, and depth would probably return an int rather than an integer with a capital I. A formal specification is a description of the component that is written in a formal language, like mathematics. However, if the word mathematics makes you uneasy, just consider a formal language as one that a computer can understand. Some examples of formal specification languages are Z, Resolve, JML, which is the Java modeling language, and Spec Sharp, which is a specification language for C#. Okay, here's the same stack interface we saw just a few slides back. And here is a formal specification for the stack component. Don't be put off by the notation. I'll explain it as we go along. For now, notice the model clause. It says that we are modeling stack objects with mathematical sequences. All this means is that we're going to treat a stack like a sequence. The first element in the sequence is going to represent the element at the top of the stack, and the last element in the sequence is going to represent the element at the bottom of the stack. Now we're going to use the formal specification we just saw to trace through some code. This is going to be a very simple piece of code, but I don't want to show you the implementation just yet. Before we see the implementation, we're going to figure out what value we should get from the code just based on the informal specification you see here. When we call this operation, let's assume that S is a stack containing elements 5, 6, and 8, where 5 is the element at the top of the stack. Furthermore, let's assume that T is a stack containing elements 4 and 3. Remember, we're representing the stacks as mathematical sequences, where the first element in the sequence is the element at the top of the stack. If we trace through the code with these initial values of S and T, what values do we expect for our final values of S and T? This should be fairly easy, but I'll give you 10 seconds to answer starting from now. The answer is, of course, S equals 6 and 8, and T equals 5, 4, and 3. Now let's see the implementation we're going to use. I said it was simple, and it is. Two statements. One pops the top element from the stack S and stores it in a temporary variable, and the other pushes the value in that temporary variable onto the top of the stack T. Here we have both our starting values and the values we expect based on the specification. Now we have to figure out if the code we have written will get us to those expected values. The first statement here is an assignment. We're assigning the result of the pop operation to the variable temp. But we don't know the code for the pop operation. And this is the point. We don't need to know the code for the pop operation because we have its specification, and components are usable solely on the basis of their specification. So let's look at the specification for the pop operation. The specification for the pop operation has a requires clause and an ensures clause. A requires clause is a precondition. It tells you what needs to be true in order for you, the client, to call the operation. In this case, the precondition is saying that the current object denoted by this cannot be empty. In our code, the stack object S that invokes the pop operation will correspond to the current object in pop. Therefore, the precondition is saying that S cannot be empty. Well, S is not empty. It has 3 elements, so we can proceed. Note that if S were empty, we could not proceed, and therefore we would not be able to prove that the value we obtained with the code was the same as the value we expected. Okay, let's move on. The ensures clause is a postcondition. A postcondition tells you what will be true after the operation is finished, provided that you called it correctly with arguments that did not violate the precondition. This postcondition says that the value of the current object after the call is equal to the value of the current object before the call, except that the first element has been removed. That hash symbol in front of this can be read the old value of this, meaning the value of this before the call. It's there because we want the postcondition to indicate how the state of the program changes as a result of calling the operation. Because S corresponds to the current object, and S is originally the sequence 568, this means that after the call, S will be the sequence 68. Remember, the first element of the sequence represents the top of the stack. So this means that S has lost its top element, which makes sense for a pop operation. The second part of the postcondition says that the result, the object returned by the operation, is the first element of the current object. In this case, the top element of the stack. Therefore, after the operation, S is 68 and temp is 5. But don't forget about T. Even though T wasn't modified, we still have to include it in our state. So the values of the variables in state 2 look like this. Now let's go from state 2 to state 3. To do that, we have to bring up the specification for push. The specification for push has no precondition. That means that we'll always get to the next state. In the postcondition, the current object this now corresponds to the stack T, because T is invoking the method. Furthermore, the variable element in the postcondition corresponds to the variable temp that's being passed in as a parameter. Therefore, the postcondition says that the value of T after the call is equal to the singleton sequence containing the original value of temp plus or concatenated with the original value of t. The original value of temp is 5, and the original value of t is the sequence 4, 3. Therefore, the new value of t is going to be the sequence 5, 4, 3. The second part of the postcondition says that the new value of temp, the value of temp after the call, is equal to question mark, question mark. What does that mean? Well, that means that the new value of temp is unspecified. You can think of unspecified as having a similar meaning to uninitialized. That is, you shouldn't use the variable temp again until you initialize it or assign to it with a new value. Okay, so now we have our new state. S does not change, T is the sequence 5, 4, 3, and temp is unspecified. Now we can answer the question, does the code give us what we expected based on the specification of the transfer top method? And the answer is yes. S and T are what we expected them to be. But now it's time for another question. And the question is, by doing this tracing table, what have we proved? Please pause the video and try to tell me what this trace of the transfer top operation has proved. Ready? The answer is a bit tricky, so I'll write it out on the slide. By tracing through this code, we have proved that the code is correct with respect to the specification for the one particular input that we looked at. What does this mean? Effectively, this means that we have proven roughly the same thing that a single test case would have proven, that the actual value equals the expected value for one particular test case, or for one particular input. Of course, if you choose your test cases wisely, you can have a good deal of confidence that your code is correct, but you just can't prove it in general for all arbitrary input. It's the same thing here. However, please note that when you trace through code by hand in this way, or if you have a computer program that can trace through code, it's still different from testing, because in testing, you have to run your program. In tracing, you are not running your program. Why and when is this important? Well, it's particularly important in critical systems like space shuttle software or air traffic control systems or certain medical system software, where you want to make sure that the system works before you actually have to run the system. Here's another look at the formal specification. Formal specifications can sometimes be tricky to write, but with a reasonable amount of effort, they're not that difficult to read. Let's compare some of the benefits and drawbacks of both formal and informal specifications. Informal specifications are easier to write than formal specifications. Furthermore, understanding them and writing them doesn't require a heavy math background. Another benefit of informal specifications is that pictures and diagrams often help users to understand the big picture relatively quickly. On the negative side, informal specifications can often be vague or ambiguous, and they definitely cannot be understood by computer programs. Formal specifications tend to be more concise than informal specifications. They're always precise and unambiguous. And perhaps their biggest benefit is that they can be understood by other computer programs, so that people can write tools that utilize them. Tools that use formal specifications can help you analyze, test, or verify your code. On the negative side, understanding formal specifications does require some basic math knowledge. but it doesn't require a lot, as we saw in the stack example. In contrast to this, writing a good formal specification for a component really does require a strong math background. And that's an overview of specification, both formal and informal. In the next video, we'll talk about verification. That is, we'll talk about how to prove code is correct for arbitrary input to an operation.